Okay, Bismillahirrahmanirrahim. These are a couple of examples about conduction in preparation for the exam. You have a wall, plain wall, infinite in this direction and in this direction, and finite in this direction. So the width is it's given here as 100 millimeters. So this is like 0.01 meter. Don't get fooled with the units. And here are the properties: density, specific heat, and thermoconductivity. And there's an initial temperature. So the initial temperature is 200 Celsius. It is to be heated to a final temperature of 550, but 550 says it's the minimum. So if the T infinity is the convection temperature is 800, so we expect the thing to heat up and then the minimum temperature to be along the center line. So if the temperature at the center line reaches 500, then this would be the minimum. Okay, so there are combustion product gases blowing at with a heat transfer coefficient 250 and an 800 Celsius temperature. So what is the time? There are a few assumptions here. Of course, you have to say, and this is to use the information. Chapter 5. This is 1D conduction in this direction only, and that the properties are not a function of temperature, so constant properties, and there's no radiation, just convection, and there's symmetric heating. So the conditions here are the same as the conditions here. First thing to do is to calculate the Biot number, which is HL over K, and we have here, this is this is 250. L is the characteristic length, has to do with the ability to store the energy. So this L for a plain wall is just the width of the wall. We'll see in the next example, which involves a cylinder, that this is a bit different. And K is given at 48, and this will give us a Biot number of 52%, 52.52. Okay, so the spatial effects lumped capacitance method cannot be used, so we have to use table 5.1, I think. And at this Biot number, this is 5.1, it's in between 5 and 6. So I'm gonna eyeball it, يعني مو شرط بالضبط. So you have zeta at around 660 or 661.661, and you have C1 around 1.072 something. Let's take it this way. So this is approximate. And you have, according to the temperatures, this is the dimensionless temperature difference. So this is theta over theta I, which is T minus T infinity over T I minus T infinity. And you have these as 550 minus 800 divided by 200 minus 800, which would give you 0.41517. Now, assume the Fourier number to be greater than 0.2, and note that the minimum temperature is, like we said, along the center line. So we'll use the 1D approximation, one-term approximation, which would give theta naught star as C1 exponential of minus zeta squared Fourier number. From that, I'll know that Fourier number is minus هذا كله, so zeta 1 squared natural log of theta naught star divided by C1. Okay. If you multiply out all of these, take natural log, this would give, this is 2.17. And from the definition of the Fourier number, so if you have Fourier number as alpha t2 L2 alpha t L2, this will give you t as Fourier number L squared divided by alpha, and this would be 2.17 0.1 divided by 2, because this is the L, divided by 48 divided by الأخوان هذيل, so this is 78 33 or 30 times 550. Okay, they're كلهم divided, and this would give you 487 seconds. Okay. Okay, a couple of assumptions, but this is the final answer, roughly. Okay, these are not exact. These are not exact. Other question which has to do with the lumped capacitance method and maybe ways to use it. We have a cylinder that is 160 centimeter long, 30 centimeter across, and it weighs 100 kilograms. So it's placed in an environment at 25 and environment of 20 Celsius, and the temperature is initially at 37, and we want to see the time it takes this cylinder to reach a final temperature of 25 in a 20 degrees Celsius environment. So we'll see, we'll assume a heat transfer coefficient of 8 watt per meter square Kelvin, and we'll assume the lumped capacitance method. Okay. It is not exactly lumped capacitance method assumption, but I'm going to use it anyway. You'll see why later. So you have to calculate a few things here. You have to calculate like a surface area for the cylinder, so that you get the density, you get the characteristic length. You have to, this is the perimeter times the length. So this guy is plus the areas of the top and bottom, assuming that everything is exposed to this air. So this is, you have this number, whatever, and the volume is just pi over 4 d square h, which is whatever, and you have the characteristic length, which is just the volume divided by the area, the surface area, which is given by whatever, and you have rho, which is the mass divided by the volume, which you calculated here. The volume, you have 100 kilograms divided by volume, whatever volume, and you have alpha, which is the thermal diffusivity, is K over rho Cp, which is given by a copper, right? So copper, so pure copper, 401 divided by 8933 or 30, forgot, and the Cp is 387. So this is given by, this is like 1.1667 7 or 6 something. So meter square per second. And then for a convection only, you have temperature, time, as rho C V divided by HA for the surface area, and natural log of Ti minus T infinity. I think this is equation 5 in your book, in my book at least, T minus T infinity, which is equal to whatever. You just substitute and get this. If the lumped capacitance method is not to be used, then you'll have to see the center temperature. You have to know exactly which 25 degrees Celsius at the center, ni, ولا at the center ni, ولا at the center, ولا at the surface. Okay. If it's at the surface, then the coldest would be ni, the farthest, and you have to have the plane wall and the cylinder multiplying each other. Okay, like a multi-dimensional effect. But this is why I said let's solve it using the lumped capacitance method. I hope this helps. I'll upload a couple more maybe problems about chapter 3, chapter 2, and Allah Sahel.